So our last topic in thermodynamics is phase changes. And phase changes are something that we definitely talked about last year in first year chemistry. And the only difference in this unit is that we're going to quantify it. We're going to put numbers down in terms of how much energy it will take to, melt a gram of water or boil, 100 kilograms of mercury, something like that. So the main new vocabulary terms that we may encounter are delta H of vaporization and delta H of fusion. Vaporization, or this term right here, refers to the amount of energy needed to go from a liquid to a gas or a gas to a liquid. So this is the amount of energy that you would need to put in to go from a liquid to a gas, or the amount of energy that would need to be removed to go from a gas to a liquid. It will be in kilojoules per mole. That's the unit. So then if you wanted to know how much energy would you need to add to boil 4 moles of water, you would multiply it by the delta H of vaporization of water. The next one is delta H of fusion, and this is going from a solid to a liquid or a liquid to a solid. So this is the amount of energy that you would need to put in to go from solid to liquid, or the energy removed to go from a liquid to a solid, or freezing. It's also listed in kilojoules per mole, so you would just multiply by the number of moles to get the kilojoules. On the right-hand side is another picture of with all the different names of the phase changes, and I'm pretty sure that you remember all of them. The 2 that were new last year were sublimation and deposition. Sublimation occurs when a solid goes right to a gaseous state, and deposition is the opposite of that, gas right to solid. It happens for most substances, but usually at very low pressures and low temperatures. Okay, so this just shows us a little comparison about these numbers for different substances. And so what's really interesting is trying to explain why. That's a very common AP question, is giving you the data, saying mercury has a higher delta H of vaporization than water, explain why. And what you need to think about is, so what type of attractions are being overcome or broken in order to make that phase change? If you think about butane is completely nonpolar. So the only intermolecular forces here are London dispersion forces. That's what needs to be overcome for it to go from a solid to a liquid and a liquid to a gas. Well, those London dispersion forces are the weakest intermolecular forces, and so you can see it has the lowest of all the delta H's. Diethyl ether would have dipole forces, a little bit stronger. Water would have hydrogen bonding forces, even stronger yet. And mercury, what is holding mercury together? Well, that's the metallic bond. And bonds are always stronger than intermolecular forces. So therefore, the amount of energy needed to boil mercury is going to be more than the energy needed to boil water. So this is a heating or cooling curve, and it just shows one major feature that it will show is this straight line. And what does that straight line represent? Well, if you look at it, it's where heat is being added, but the temperature is not changing, and that must mean a phase change. So anytime you see a heating curve and you see a flat line, a slope with, or a line with no slope, this means that a phase change is occurring. All the other times, we're just heating up liquid water, or we're heating up gaseous water. And in order to find how much energy, right, when we relate energy to temperature change, that's MC delta T. So now we're going to do this sample problem. This is going to be a lot of arithmetic here. It says calculate the enthalpy change on converting 1 mole of ice at 125 to steam, ice at negative 25 to steam at 125. And then it gives us gives us all sorts of data. So basically what we're doing is we're going to find out how much heat needs to be added in order to do the processes that are on this graph. Going from A to B is increasing the temperature of ice by 25 degrees Celsius. B to C is melting the ice. C to D is heating liquid water from 0 degrees Celsius to 100 degrees Celsius. D to E is boiling the water, making the phase change to a vapor. And E to F is increasing the temperature of the vapor to 125 degrees Celsius. So I'm just going to break that down, right? A to B, this was increasing the temperature of the ice from negative 25 to 0. Anytime that you are changing the temperature, that's when we're going to use MC delta T, right? It tells us 1 mole. And sometimes we will need to use that mole, or we might need to use the mass. 1 mole of water is 18.016 grams. So that's what I will use for my mass. The specific heat, that's what C is, of ice, is 2.03. And this is really important that we take a look at the, units. It's joules per gram times Kelvin, and then we would be increasing its temperature 25 Kelvin. When we multiply those three together, we get 914.312 joules, right? Making sure that my units cancel out. When I add everything together, I'm going to have to add all the joules or all kilojoules, because I can see in the next one from B to C, that is the delta H of fusion of the water. And according to the table, it is, let me erase that. It is 6.01 kilojoules per mole. And so 6.01 kilojoules per mole times 1.00 moles equals 6.01 kilojoules. So I'm going to have to do something to that. If I'm going to need to add them all up, I should change that maybe to just regular joules. So 6,010 joules. C to D. Look at C to D. That is increasing the temperature of liquid water. So that's MC delta T. Again, my mass is 18.016 grams. My C is that 4.18 joules per gram dot Kelvin, and the Kelvin is 100 Kelvin, and that equals 7530.68 joules. D to E is the delta H of vaporization. This is when I'm actually boiling the water. So the delta H of vaporization, and according to the problem, it is 40.67 kilojoules per mole. And that's, of course, times the 1.00 moles of water that we are changing from a liquid to a gas. And in joules, so I'm going to, obviously it's 40.67 kilojoules or 40,670 joules. And then E to F is, again, we're just changing the temperature. The mass is 18.016 grams. The specific heat of gaseous water is 1.84 joules per gram dot Kelvin, and I'm increasing it 25 Kelvin, and this comes out to 828.736 joules. I add all these up because I have made them all the same unit here, and I get 55,953 joules, or 55.95 kilojoules. Okay, so it's a lot of sort of tedious work here. But if you can do this problem, that means you can do any others, because there would be a lot less algebra or math involved. And could you do this in a multiple choice question? It would be tough because there would be a lot of mathematics to do in your head. So certainly probably not this intense. Practice exercise 1 is a multiple choice question. What information about water is needed to calculate the enthalpy change for converting 1 mole of water at 100 degrees Celsius to liquid water at 80? So I'm going to be going from gaseous water to liquid water. So that's the delta H of vaporization. That's how much energy I would need to remove, right? And then the liquid water at 100 degrees Celsius to liquid water at 80. So I'm going to need to definitely use the delta H of vaporization and the specific heat. So these two are out. The heat of vaporization and the specific heat of, and it's liquid water, because it would be from, if you're thinking about the, here would be gaseous water, liquid water, and then there's liquid water at 80 degrees Celsius. So I would need to find the specific heat capacity of liquid water. Practice exercise 2 is very similar to the one that we did earlier. What is the enthalpy change during the process in which 100 grams of water at 50 degrees Celsius is cooled to ice at negative 30 degrees Celsius? So you're going to have to do 3 different calculations here, right? If you think about, we're starting at 50 degrees Celsius, so we're going to need to cool it down to 0 degrees Celsius and then freeze it to ice at 0 degrees Celsius, and then cool that down to ice at negative 30 degrees Celsius. So there's 3 different changes that are going on here. Remember the slanty parts, this is where we do delta H equals MC delta T. And then this right here would be the delta H of fusion, right? You can use all of the numbers that are in that first practice exercise that we did. So you should go ahead, do out all these calculations, right? The question is asking, what is the enthalpy change? So positive would mean we're adding energy, and negative would mean we are removing energy. So we would be removing energy in this case, and I got negative 60.3 kilojoules. So try to do practice exercise 2 on your own, and we'll check our answers in class.